So I was thinking about some basic computer science problems. All right, like the travel and salesman problem. And I was thinking, like, is algorithms really the best way to solve this problem? Are we confining ourselves in an arbitrary box by, sticking to binary and mathematics and algorithms? So, like, let's take node number 3 here in this little graph. And let's say we just attach a water spout to it, and everything coming out of all of these nodes are pipes. All right, and then we can pretty easily find, using this method, the shortest, or the shortest distance from node 3 to any other node on the graph. You pick the other node you're going for, in this case, let's say node 6, and you start flooding it with water. And so the first connection that'll be fully filled with water is 3 to 5, and then the next one is going to be 5 to 2, because 3 plus 2 is less than 13, is less than 10, is less than 11, is less than 11. So pretty quickly you find the shortest path here to node 6. And like the easy way to see this is you would just let the water start flowing, and then as soon as it gets to node 6 you rewind it and you just follow the path back, and you just watch it go all the way back to the beginning. Anyway, but let's say we want to do something a little bit more complicated, Let's say we're looking for the travel and salesman problem, for example. I was wondering if this would have any usefulness in finding efficient solutions to the traveling salesman problem. So let's say we have the water filling up all of the pipes, and we start and we just let it go all the way until eventually forget it. You know what's going on. Eventually, only one of these pipes is going to be left with some unfilled, like, water. Eventually, it'll be filled too, but we're going to stop it right before. And in that case, it's going to be here. And now we're going to just cut this pipe off because we don't need it, and it doesn't isolate any nodes. Since we should be able to conclude that our traveling salesman problem should still exist within the rest of the graph without that one. Why? I'll be honest, I don't really have a good reason to. I found that this works so far. Am I messing around? And if I'm wrong, then someone can show me. I would love to see, why that wouldn't work. But anyway, to continue the example to show you what this can do. So we know node 2 must be the second node in the sequence, or it must be the final node in the sequence, right? It's either going to flow here and then out and so on, or it's going to flow all the way around to node 2. No, not again. Okay, so, but we don't know which one node 2 is going to do yet. So, next, let's see. What do we want to do? Well, what we do know is that this path will be used in our traveling salesman solution. Because this is the only other path node 2 has. And so regardless, this path is being used. And because regardless this path is being used, we know that node 1 here, sorry, it's a little cut off. Node 1 is not connecting to node 3 under any circumstances. Either node 2 is connecting to node 3, or a node that doesn't connect to node 2, a completely different node is connecting to node 3. One can't connect to node 3 because then it would just form like a little loop here, and that it just wouldn't work. Or the traveling salesman wouldn't travel everywhere. So that doesn't work. So then we know that this path has to work. Node 1 will flow to node 8. And now we can consider node 8 can't float directly to node 3 either, because that would just end the cycle, and he wouldn't have traveled to all the nodes. So now the water has to flow from node 8 to node 7. And then node 7 doesn't flow directly to node 3, so no free cutoff there. And now let's go back and consider the water flows in. Okay, so 3 plus 2 is 5. Distance 6, nothing. But distance 8 does have something. Distance 9 is for this one. Distance 10 is right here, and distance 11 is here. So let's cut off distance 11 for now. Hi, editor me here. I realized in post that I made a mistake here and I cut off the pipe length, or the pipe that had length 11 from node 3, when there were longer pipes, 2 pipes that had length 13 instead. So I continued with it. So we're going to pretend instead of 11 that was actually length 14. And see that this means, so let's cut off distance 11 for now. And this puts 2 as our ending node, decisively. So node 7 is either flowing into node 5 or 6. Let's fill up the simulation with water once again. 3, and then 5. We reach 6 here. And then, looking ahead, I know that this connection actually won't be able to be used because the water's going to have to flow. No, that's not true. Actually, it could be used. So 5, and then 9, 11. Wait, 10, I meant 10. 13, right? Three plus 2 is 5, plus 8, yep, 13. So we have to cut off one of the two 13s. Cutting off this 13 means that our final answer is going to go to here, which will our final answer has to go here, cuts off access to node 3, and then flow, but cutting off node 13, or path 13 here, means that our final answer, instead, node 3 now has to flow to node 5. Node 5 now can't flow directly to node 7 because then traveling salesman wouldn't have a complete path. So it has to flow instead to node 4, to node 5, 6, to node 7. And now we have a reasonably efficient solution to the traveling salesman problem using water. The reason I bring this up isn't because this is, or I don't know if this is really an efficient way of finding the best solution to the traveling salesman problem. I don't even know if this is the best solution to this traveling salesman problem. I solved this, during the recording. I hadn't solved this problem before, or like this particular version. But like the reason that I recorded this, I thought I'd upload this to the internet, and because I found this really interesting, is with water, it seems a lot simpler to find efficient solutions to the traveling salesman problem than with algorithms or something like that. And I just wanted to highlight that maybe the way that we're trying to solve these problems is really inefficient. We're like sitting here looking at it with the mathematical binaries, zeros and ones. We're using only the mathematics, zeros, ones. It has to be an algorithm. It has all of these constraints. And we don't even know if P equals NP. We haven't even fully figured out all the math aspect of it, but I think we're constraining ourselves too much when trying to solve these problems, because I think it's a lot easier to solve this problem, the traveling salesman problem, if you just watch, if you view it as the system of pipes and watch water flow and then kind of like trace backwards to see, well, watch as the water takes the most efficient path. Because whereas a computer would, in order to simulate this, it would have to be like moving between like, it would flow out here and then it would flow out here and it would like start splitting and it would be doing this and this and it pretend it's doing them at the same time, but actually it's just jumping back and forth between these different paths, you know, constantly moving between all these different paths, and it's all quite inefficient. Instead, water is capable of moving between all of the paths at the same time. And so maybe there's better ways of using electricity or something like that. I don't know, but I'm just not happy with how I see we're trying to solve this problem right now using these algorithms that are just stuck in zeros and ones when there could exist much more efficient solutions, like, you know, that maybe aren't a traditional computer, but, you know, hypothetically speaking, right? You could build a computer out of water to solve this kind of problem. Would it be efficient? Of course not. But, you know, hypothetically, maybe there's other ways of solving these problems that lie outside of the basic binary and like objective and math kind of logic and OR gates that we use. You know, maybe we should explore those solutions a little bit more. Anyway, that was all I had to say.